All right, in today's video, we'll try to model the knapsack problem as an optimization problem. But first things first, let's understand what a knapsack problem is. So this is an image that we've taken from Wikipedia. Now imagine that there is a sack which has a weight limit of 15 kgs, and we have been given 5 bars. So the first one is this green bar, which has a total worth of $4 and it's 12 kgs. The second is a white bar worth of $2, but its weight is 1 kg, and so on and so forth. So we have 5 such bars. For each bar, there is a value associated with it, and then there is the weight. And now our objective is to maximize the total value of items in this knapsack. So what we, in short, what we want to try to do is we want to gain the most profit by packing this knapsack appropriately. So that is the problem. And now the data. For the data, we are going to create a list of tuples. Uh, this list will be like this. The first item in the tuple will be the value of associated with the bar. The second one would be the weight. And then finally, the third one is the color. So for example, this green bar, $4, 12 kgs, and the color green. This is how the data will look like. And then finally, we also add the maximum weight capacity for this knapsack. In this case, it is 15. Now, there is one distinction in this problem that we will try to solve. That is, we cannot put partial bars into this knapsack. Either we use this entire bar or we do not use the bar at all. So what that means is this becomes a one null knapsack problem. One meaning that put this bar, we'll put this bar in the knapsack. A null means we will not put this bar in the knapsack. Once now that we have decided that this is going to be a one null knapsack problem, let's try to frame this problem as an optimization problem. So in the first case, what we need to decide is the decision variables. Now, as we said, it's a one null knapsack problem. That means for each of the bar that we have, for each of the bar that we have here, we would want to have a decision of one or null, meaning keep it in the knapsack or don't keep it in the knapsack. So the first thing that we would want to declare is the decision variables. Now this decision variables, we can declare it multiple ways. In this example, however, we will declare it as an LP variable dictionary. Now, this is the item. Item will be associated with each bar. The number of decision variables that we want to have is the number of items in that bag. And we would want to have the category as binary because we want to either keep this article in the bag or don't keep this article in the knapsack. All right, so now comes the part where we would want to define an objective function for this optimization. Now the objective function is our North Star. We need to know which direction do we want to go while optimizing our problem. In this case, what we would really want to do is to maximize the profit in our knapsack. And what that means is we would want to maximize this equation. So this equation is the decision variable x of gray into the value of gray. So what does this mean? It means that we would want to have the decision variable x of gray. This is something that the optimization engine will decide. And then the value of gray is the monetary value that we associate with this bar. Here, 2 is the bar. If we include all of these articles in this knapsack, then in that case, all of our decision variables are going to be 1, and the value is going to be 1 into the value of that bar, 1 into the value of the green bar, so on and so forth. And of course, it is going to go above 15 kgs. But what we would want to tell our optimization problem to do is maximize this value. And this is how we can denote it. So we would want to maximize the summation for across C, where C is green, blue, yellow, red, gray. We would want to maximize the decision variable x of C into the value of C across all the items. And once we have modeled this equation, once we have modeled this mathematically, we can pretty much translate it into pulp. In this case, we first need to define the LP problem, and we would want to set it up with an objective to maximize it. Second step is we would want to add the objective function, and for that we would want to do x of I, which is the decision variables, into items of I of 0. Now I of 0, in this case, it is the value. So x of I into items of I of 0 across all items, and this is how we can declare our objective function. And now something about the constraints. So in this example, we have only one constraint, at least for now. The constraint is that the sum of weights of the items in the knapsack must be less than or equal to the maximum weight capacity of the knapsack, which is 15 kgs. In sense, what we would want to do is similar to this objective function equation that we discussed. We would just want to change one tiny value, and that is W of C. So what that means is we would want to, across the summation of C, where C is green, blue, so on and so forth, the decision variable x of C into now the weight of the bar and the summation across all items should be less than or equal to 15. Right? In that case, what we would do is the constraint now will be x of I, the decision variable, into items of I of 1. And in our case, I of 1 is this. So it is the weight of the item. So x of I into items of I of 1, this is the constraint. The summation of across all items should be less than or equal to bin capacity. Now this is very important. In this case, because it is a constraint, we would want to add symbol, which is less than or equal to the bin capacity. And this becomes our constraint. And then finally, if we print out the problem is going to look something like this. So we would want to maximize the decision variable into the value of the bar, and this is subject to the constraint of maximum capacity that we just discussed. And the variables, the decision variables, item of 0, should be an integer, and it should be between 0 and 1. And now it comes time to solve the problem, and we can pretty much solve the problem simply by calling dot solve. We can print the status of this problem. So this is the logs of the solver, and the status is optimal. So it was very simply able to solve this problem. And we will also now print out some more information about the solution. And the items that are used is red, blue, yellow, gray. Now here the used capacity is 8 out of 15 kgs, and the profit is 15. So this is one way that we can solve the knapsack problem. Now what if we would want to add some other constraints? For example, we say the maximum number of items should be equal to only 2. That is, in this case now, the summation of decision variables, the summation of decision variables should be equal to 2, right? Because only two because only two bars can be chosen in the knapsack. And we can add this constraint like this. We will do summation across all decision variables should be less than or equal to 2. And this is how we can keep on iterating over our problem and adding more constraint as and when we see fit.